ACE 111 Lecture 3 Set 4, FPGA or Field Programmable Logic Gate Arrays. Let's go back to the example we had in an earlier lecture where we had a 4-bit multiplexer based on 2 input muxes. So here we have 2-bit input muxes, and then we are concatenating these 2 in series with another 3 of them to make a 4-bit mux. And now what happens is that assuming that I'm going to use this for making logic, what happens is that if the selector bits are in different situations, basically the different combinations, it can tell us which of these bits here is going to show up at the output. And that we could use to implement a logic. For example, let's assume that the logic that I want to implement is an XOR gate. So XOR gate is defined here, 0, 1, 1, 0. And then what happens is that if I do this, connect these to 0 and I connect these to logic 1, what happens is that every time I have this combination, say 0, 0, the proper value, which is this one, is going to come out and be shown as a logic. As another example, if I'm going to define this time and function, what happens is that I could just go ahead and make a different assignment for the values here. Basically, this will be the 1, and then these will be the 0. So here we see that, using this multiplexer array, we have been able to implement, using lookup table, different types of logic, but it's a different type of lookup table than what we had with the PLAs earlier. What we just saw in terms of multiplexer is a logic element or configurable logic block, but in typical field programmable gate devices, we have also input-output elements that input things to those logic blocks and then output from it. So we go to input-output pins in certain parts of the program, and we also have programmable interconnects. Other building blocks are also possible. Even modern FPGAs may even have hardcore processor or software processor in them. But for the purposes of this class, we're just going to focus on this most basic model of an FPGA, which I'm showing here. We have the logic elements and then the I/O logic that connects that, and then the interconnects that are connecting those. The LUTs or lookup tables are flip-flops and multiplexers. Flip-flops are storing the values of the combinational logic. The multiplexers are the ones I just showed earlier. They connect LUTs, the lookup tables, and flip-flops to make the different types of logic for us. One of the most basic Altera Cyclone devices has 1 4-input LUT, 1-bit output, and 1 combinational output. And then these logic arrays are connected, as you see here, using programmable interconnect. Typically, these are switches that can connect the different ports coming in from these sides to different parts here. So they could actually connect different logic blocks or configurable logic blocks to each other. The mux as a lookup we just saw earlier, you could also reduce the size if you see that. And the ARIA2 device family that we are using in this class has a similar structure, but it has 6 input LUTs. So we, instead of those 4-bit muxes, we have 6-bit muxes with 2-bit muxes each. But then we also have some adders, because addition is a function that is very commonly used, so that actually can accelerate things for us. And then we also have the logic that connects this combinational part, which we make in the LUTs, to a sequential register part. And this can help us make combinational and sequential logic, as we will be seeing further. So Boolean equations can be represented by truth table, and the truth tables are the computational part of the FPGA, and LUTs is implementing that. Here is an example of a lookup table using mux. We are not showing those different hierarchies of a multiplexer, just showing 1/8 8-bit multiplexer that is making the selection between the 8 for making the Boolean expression based on A, B, and C. The structure is again seen here, but of course, if you have 6 inputs, we have a hierarchy of the multiplexers that are 2 bits, as shown here. So 4 to 1, we have 7 of them to make a 6-bit input LUTs. And the device has a large array of these devices, but it also has some other elements because, you know, there are, for example, elements for signal processing, the DSP units and other units, and the blocks for phase lock loop and other elements that are commonly used in design that are board in one device. The next lecture is going through the design flow for FPGA and application-specific integrated circuits.